Today, we're diving into the surprisingly vast world of graph theory, a field that, believe it or not, secretly powers so much of our digital lives. So let's get right into it.
Okay, let's kick things off with a bit of a puzzle. You've got a navigation app, a social network, and a number game. On the surface, they seem completely different, right? But underneath it all, they share this deep, fundamental connection that computer scientists use to solve all kinds of problems.
The answer is that they're all networks. You can think of every single one of them as a collection of interconnected points. And this simple idea is what we call a graph. Now, when we say graph, we're not talking about charts and diagrams from a business meeting. It's a really powerful way of seeing the relationships between things. And honestly, once you start looking for them, you start seeing these graphs absolutely everywhere. They're often hiding in plain sight, modeling the world all around us in some pretty elegant ways. I mean, think about Google Maps. Each intersection is just a point or a vertex, and the roads connecting them are the lines or edges. It's the exact same idea for Facebook. You're a vertex, and your friendships are the edges that connect you to other people. It's just a really natural way to map out these systems. But here's where it gets really interesting, because graph theory shows up in places you would never, ever expect. Like, for instance, a classic Sudoku puzzle. To a computer, this isn't a number puzzle at all. It's a coloring problem. Here's how it thinks about it. Each of the 81 squares is a vertex. An edge connects any two squares that are in the same row, column, or box, basically any two squares that can't have the same number. And the numbers 1 through 9? The computer just treats them as colors. So the goal is simple. Color in the empty vertices so that no two connected vertices have the same color. This is a classic, well-understood graph problem, and computers are fantastic at solving it. So, to really talk about these networks properly, we need a shared language. And luckily, it's built on just a few core concepts that unlock everything else. It all boils down to two super simple things: the points, which we call vertices or sometimes nodes, and the lines connecting them, which we call edges. That's it. Seriously, the entire field is built on that one foundation. Now, a path is pretty much what it sounds like. It's a route you can take through the graph by following the edges from one vertex to another. And if that path eventually leads you right back to where you started, boom, you've just made a cycle. In social network terms, this is really easy to picture. Your direct friends are your neighbors. And the total number of friends you have, that's your degree. It's a simple but really powerful way to measure how connected any single point is within the bigger network. And this brings us to a really key property: connectivity. Is the network one big, cohesive group, or is it broken up into a bunch of isolated islands? If you can find a path between any two vertices in the whole graph, then we say it's connected. Okay, so that's all great as an idea, but how does this abstract concept of points and lines actually get stored inside a computer? How do you turn a drawing into data it can actually process? Well, computers usually use one of two main ways. The first is called an adjacency matrix. You can think of it like a big grid where a 1 marks a connection between 2 points. The other way is an adjacency list, which is maybe more intuitive. For each point, you just make a list of all of its direct neighbors. So which one is better? Well, for most real-world problems, the adjacency list wins, hands down. And here's why. Most big networks are what we call sparse. Think about Facebook again. There are billions of vertices, but you're only connected to a few hundred or maybe 1,000 of them. An adjacency matrix for that would be a gigantic grid that's almost entirely filled with zeros, a colossal waste of memory. The list, on the other hand, only stores the connections that actually exist, which makes it way, way more efficient. All right, now that we have the fundamentals down, let's look at some of the really profound and fascinating problems that graphs help us explore. Some are solved, and some, well, not so much. So here's a classic question. Imagine you're trying to trace a drawing without lifting your pen and without going back over any lines you've already drawn. The question is, can you find a path that travels along every single edge in the network exactly one time? And the answer to that one is yes, we can figure this out. Computer scientists have known for a long time how to solve this problem efficiently. There's a reliable, fast algorithm that just gives you the answer. It's a solved problem. But now watch this. Let's change the question just a tiny bit. Instead of visiting every edge once, what if we want to visit every vertex, every city, every person on a social network exactly once? This is famously known as the traveling salesperson problem. And suddenly,
everything changes. Just by swapping that one word, edge, for a vertex, we've gone from a solvable puzzle to one of the most famously difficult and unsolved problems in all of computer science. There is no known efficient way to solve this. None.
And the difference in difficulty is just staggering. The best algorithms we have for this problem run in what we call exponential time. That means for a graph with just a few dozen vertices, a computer could literally take longer than the age of the universe to find the one best solution. It becomes impossibly slow, incredibly fast. And this isn't just some minor academic puzzle. Finding a fast algorithm for the visit every vertex problem would be revolutionary. You'd solve a major open question in math, you'd probably be given every computer science award there is, and it would have massive implications for logistics, bioinformatics, circuit design, you name it.
And that really is the magic and the mystery of graph theory. It gives us this incredible language to describe the world, but it also shows us that the line between what is easy and what is fundamentally profoundly difficult can be as thin as a single word. It makes you wonder, what other simple questions out there are hiding universe-sized complexities?